Welcome back to The Explainer. Today, we are tackling one of the absolute strangest, most paradoxical phenomena in the entire cosmos. We're looking at gravity's infinite reach, the mystery of black holes. We're going to unpack the underlying mechanics of these dark cosmic engines, examine exactly how they manage to bend the very fabric of our reality, and explore how astrophysicists are actually managing to map and study entities that are defined entirely by their absolute invisibility. The physics at play here really push the boundaries of general relativity and quantum mechanics, literally taking us to the very edge of what is currently understood about the universe. So, let's dive right in. So, what exactly are we dealing with? A black hole is an object so incredibly powerful that nothing, and I mean absolutely nothing, not even light can escape from it. To really grasp the sheer magnitude of this, it helps to think about it through the concept of escape velocity. You know, here on Earth, a rocket needs to reach roughly 11 kilometers per second just to break free of our planet's gravitational pull. But gravity is proportional to mass and density. When an object gets dense enough, the velocity you need to escape its surface eventually exceeds the speed of light, which is roughly 300,000 kilometers per second. And because the speed of light is the absolute cosmic speed limit, nothing in the universe can travel fast enough to get away. The object effectively becomes completely, causally disconnected from the rest of the observable universe. It's just gone.
Section 1. Death of a massive star.
Now, the creation of these black holes is tied to a super dramatic breakdown of what astrophysicists call hydrostatic equilibrium. Think of it like a giant cosmic tug-of-war. For millions of years, a massive star, usually one that's at least 8 to 10 times the mass of our own sun, maintains this really delicate balancing act. Deep down in its core, nuclear fusion is producing an immense outward thermal pressure. And this outward force perfectly pushes back against the staggering inward crush of the star's own gravity. But as the star runs out of its lighter elements and starts fusing heavier ones, it eventually produces an iron core. And here's the catch. Iron fusion actually absorbs energy instead of releasing it. That means that crucial outward pressure suddenly just drops to zero. In a fraction of a second, gravity wins that billions of years long tug-of-war. The star's outer layers violently collapse inward at a huge fraction of the speed of light. They slam into that dense core and rebound in a massive supernova explosion. Meanwhile, that inner core just keeps collapsing under its own weight, compressing an entire sun's worth of matter into an infinitely small, infinitely dense point. And that is what we call a singularity.
Section 2. The event horizon boundary.
Right surrounding that central singularity is the event horizon. This is the exact boundary where escape becomes mathematically impossible. Now, it's absolutely crucial to understand that the event horizon isn't a physical surface. It's not a solid wall you'd crash into. It's a purely mathematical threshold in space-time. Once an object, or even a single photon of light, crosses this line, the curvature of space-time is so extreme that all possible forward paths lead only one way, straight toward the singularity at the center. Space itself is effectively flowing inward faster than the speed of light. If you were a traveler crossing the event horizon, nothing would visually seem to block your path, but your timeline and your trajectory, they are permanently, inevitably locked to that center point.
Section 3. Debunking the vacuum myth. Okay, we need to clear something up because there is a very persistent sci-fi trope that paints black holes as these giant cosmic vacuum cleaners, just aggressively sweeping up nearby stars and dragging in everything around them. But the astrophysical reality, it's just governed by standard orbital mechanics. A black hole has the exact same gravitational properties as any other object of identical mass. Let's put it this way. If our sun were magically replaced right now by a black hole of the exact same mass, Earth would not get sucked in. No way. Our planet would just keep orbiting in the exact same trajectory, with the exact same 365-day year, because the central mass anchoring our solar system hasn't actually changed. A black hole's immense gravity only becomes a threat if an object loses its angular momentum and drifts extraordinarily close to that event horizon. As long as you're at a safe distance, it just acts like a completely normal, standard gravitational anchor.
Section 4. Bending space and time.
But what if you do get dangerously close to that threshold? Well, that's where the mind-bending physics of general relativity kick in. Because a black hole packs so much immense mass into such a tiny volume, it deeply, deeply warps the four-dimensional fabric of spacetime around it. One of the coolest observable consequences of this is called gravitational lensing. Basically, as light from distant background stars travels past the black hole, its path is physically bent by the warped space. It creates this wild visual halo, or a distorted ring of light. And it gets crazier, because relativity dictates that gravity also affects the flow of time.
As an object gets closer to that intense gravitational well, it experiences significant time dilation. If you were sitting in a safe, distant orbit, watching a clock fall toward the event horizon, it would appear to tick slower, and theoretically, it would freeze entirely right at the boundary. It really shows just how profoundly gravity can manipulate the fundamental dimensions of reality.
Section 5. Supermassive Scale. So far, we've mostly been talking about stellar mass black holes, the ones born from collapsing stars. But the cosmos hides something much, much bigger: supermassive black holes. These absolute leviathans possess masses ranging from millions to tens of billions of times heavier than our own sun. And they aren't just rogue anomalies wandering through the void, either. They are the fundamental gravitational engines sitting at the exact center of almost every large galaxy in the universe. That includes Sagittarius A star, which is right at the heart of our own Milky Way. Now, astrophysicists are actually still fiercely debating how these giants originated, because they're just too massive to have formed from a single star. The running theory is that they grew through a mix of devouring vast amounts of gas and merging with other black holes in the dense, chaotic early days of the universe. Their sheer scale essentially dictates the evolution, the rotation, and the entire life cycle of the very galaxies they live in. Section 6. Photographing the unseen. Now, think about this for a second. How do you study, let alone photograph, an object that emits absolutely zero light? It takes unparalleled technological ingenuity. For decades, we only knew black holes existed through mathematical proofs and by watching the super-erratic orbits of stars circling invisible dense points in space. But then, in 2019, everything changed. Astrophysicists made the massive leap from theoretical deduction to direct observation. The Event Horizon Telescope project used this incredible technique called Very Long Baseline Interferometry. Basically, they synced up a global network of radio observatories to effectively turn the entire planet Earth into one giant telescope. By aiming this huge planetary array at the supermassive black hole in the center of the galaxy M87 and crunching petabytes of data, they actually did it. They successfully resolved the black hole's shadow against the glowing accretion disk of superheated gas spinning around it. This historic, game-changing achievement visually validated Einstein's general relativity in the most extreme environment you could possibly imagine.
Black holes really represent the absolute extreme limits of the known universe. They sit precisely at that crossroads where general relativity and quantum mechanics just collide, and, right now, completely fail to reconcile with each other. They force physicists to grapple with profound concepts, like the information paradox and what space-time actually is. Ultimately, they stand as the ultimate laboratories for testing the fundamental laws of nature. So if these cosmic engines are continuing to redefine our very baseline understanding of gravity, space, and time, you have to wonder, what other paradigm-shifting secrets are just waiting to be discovered out there in the dark? Thank you so much for joining me for this explainer today. Keep asking questions, keep looking up, and I will see you in the next one.